So this next slide is an amended or an edited version submitted by Doug. And this is the only thing that I'm going to really contribute to this meeting. I'm going to tell you about, well, the state of the semiconductor industry in the 60s and 70s was discussed in our April 1st meeting, where we had almost 100 people. And so we won't repeat that. Hopefully the videos will be available soon and you can watch that online. I want to tell you what the landscape was from 1975 to 1979 when I was an application engineer and chip architect at National Semiconductor and Signetics. We didn't have any EDA tools. When there was a new chip project, we assembled a team. And the team consisted of a chipped architect, essentially a product specifier, and someone who knew logic, a detailed logic designer who could break that down into logic blocks, a circuit designer, and a test engineer. And later on, there came a draftsman who would work with the circuit designer to do the layout, routing, and placement of the integrated circuit. At least until the early 1980s, it was commonly believed that a computer could never be as efficient as a draftsman in laying out an IC. I heard that myself from the layout engineer for the Intel 8086, the most popular at the time 16-bit microprocessor. Now, none of those guys believed that Moore's Law was going to advance. They were all very, very skeptical. So they never thought that ICs would get so complex that it would literally be overwhelming, if not impossible, for a draftsman to do the layout and placement of the cells that went on the silicon die. At this point, I'd like to turn it over to Doug, who has some historical evidence. Maybe you want to come up here to show your slides to address this point of skepticism and why it was believed the computer layout and cell interconnection couldn't be as efficient as a human.
This is the picture, a map that appeared on the first issue of Lambda Magazine, which I just held up. This is actually the second issue. This was the first issue. And it was inspired by work done at Caltech. And it was, people talk about, well, what's the contribution of Carver Mead and so forth. Depending on the year, it's many different things. But at this time in his life, he had been consulting, as a advisor to Gordon Moore as far back as his days at Fairchild. Would meet with him weekly, sit down with him on a Wednesday morning before anybody showed up, and they would just chat about challenges and the technology and manufacturing and so forth. Carver, his background is in physics and always had something to contribute. When Gordon Moore sort of envisioned the Moore's Law, he merely looked at the manufacturing process, that this is what's happening. He didn't have a theory behind it. He just drew a curve of what he saw happening in the manufacturing process, and density increases at Fairchild. And in one of those meetings subsequent to this statement, Gordon asked Carver, he says, well, we keep making these transistors smaller. How small can we make them? And Carver admitted, and the reason I can tell you all this is because I did an oral history with Carver at the Computer History Museum, where I spend a lot of time these days. And it's fascinating to get these personal, one-on-one conversations going, even with people you've known for 30 or 40 years. And, in telling the story, which it won't play well here, but you can go online and read the story. And, Gordon says, well, how small can you make these? And he says, I don't know. And that conversation sent him on a path to figure out how small you could make them. And he figured after some study and working with graduate students and all that something below below 100 nanometers, below the 10th of a micron was where you're going to start to run into trouble. And there wasn't a cliff, but it just sort of became more and more difficult, and you could envision. And in fact, that's where eventually we ran into trouble. Of course, back in this time, if you look at the map, we're talking about a few years past 1963 when the design rules were maybe 5 microns or 4 microns, and we were envisioning 1/10 of a micron. So there's a long, long way in the future at that time. And so Carver became convinced that the world really was going to go down this path to ever shrinking geometries and ever growing complexity on die. And that then became his focus of research of what are we going to do when these things get so small, and how are we going to design them? And so his background was in physics. He got enthralled with the issue of design. And it took, people, it was mentioned that people were skeptical that this would ever happen. And he describes explicitly, the years he spent proselytizing, preaching that it's coming, it's smaller, and many people didn't believe him. People top level at Intel did, but not necessarily a lot. And it took him many years, and it took the industry many years to really buy into the fact that this really is going to happen. And it was really this sort of onslaught of technology that was being driven from the bottom, from the manufacturing, which finally sort of broke the back and said, we've got to do things a different way. And different people's back broke at different times. But in 1980, we got to the point where we were doing 30,000 transistors on a chip, and in 1990, 10 years later, we were doing 1 million transistors on a chip. And in that decade, people fell, right? And those of us who were involved early fell early because we wanted to promote the world of new types of designs with new types of engineers and that sort of involved. But others who had been doing it for many years took a lot longer to adapt the new methodologies and new approaches. But fundamentally, with 1980, 81 as a breaking point, that's when so many systems engineers started getting involved in IC design. There was a huge explosion in the EDA world to try to tackle this very incredible growth in complexity. And the point that was made about the layout designer at VLSI Technology, when we founded it, when we really got going in 81, we didn't have the tools yet. We envisioned the tools, but we didn't have them. And we set about building them, but in the meantime, we had to make chips and we had to do things. So we actually had draftsmen drawing on Mylar and colored pencils and laying out chips the old way. And I remember, come around 1985, somewhere in the middle of the decade, we started needing them less and less. And about the middle of 85, we said, most of you guys are gone. And we had a very explicit program. We said, we don't need you layout people anymore, except for a couple who were doing low-level cell design. And some of them went off and worked somewhere else. Some of them, were transitioned to new jobs within the company as, systems maintenance people that kept up the systems and that sort of thing, actually changed their careers in the process. But it was a major transition. That group shrunk dramatically because at that point, automation took over and said, we don't need these hand drawers anymore. And it happened at different times in different companies. And there's always room for a few, the people doing the very low-level layout and so forth. But in general, the complexity got to a point where, and the need for accuracy and perfect design and everything got to a point where you just had to do it in an automated way. And I want to come back to this picture because even though this was drawn, I didn't create it, but I took we used it as a model in this magazine cover, and it is truly is the best tool that we have in my mind to try to fathom the complexity of what semiconductor design is all about. And even looking at this, you can't believe that we design semiconductors today. Because let's look back in 1963 when chips had geometries of 25 micron. It says lambda equals 12 microns, which is sort of half of the standard width. So we had 25 micron geometries. Even then, if you took the layout, the metal lines or the poly lines, and blew the distance up between them to be the equivalent of a city block, that chip would cover the area of a small downtown area, such as San Jose. Okay, we can everybody can remember the street names. You might even get to the point where you remember every house or building on every street, and you can kind of keep it in your head, and that's all good. By 78, this time, approaching the crossover period, we were confused about the button, and now the complexity of the chips blew up to be the size of the Bay Area. Well, even then, we still weren't using very complicated tools. So we were laying out street systems, by then probably in 2-level metal, And and guess what? Build freeways, and we had to get all that just right. And when we made it, it had to be perfect. There couldn't be any errors. Pretty big challenge, but because we had armies of guys crawling over plots and so forth, and after several iterations, we made it work. Well, in this analogy, we took it up to the 1990s, covering the North American continent. And in today's technology, we are building what, 6, 8, 9 levels of metal, the equivalent which, if you explode in the same way, would cover the Earth. And we're designing them not from scratch, but in a way that they essentially work the first time. I mean, we can't even design modify a street going down, middle of the city and get it right the first time. And we today are successfully designing chips of this kind of complexity. It's unbelievable. And the only way we do it is because of we use huge building blocks. We take, cities and just plop them down, microprocessors. And then we build freeways between those cities to another microprocessor. And then we build them to, a huge memory bank, whatever analogy you want to draw there. And so we use building blocks because there's no way, going back to Art's hierarchical thing, there's no way we're going to design every chip from scratch. We take, well, this city is perfect and this city is perfect, and so we'll put those down, and this memory bank is perfect, so we're going to put that down, and we just have to make sure the connections between them are correct. But the bottom line is we then manufacture a product which has this kind of complexity, and most of them work. And it's, when you think of it in those terms, it is just unbelievable what we have accomplished in terms of design, let alone the manufacturing process. And it's that sort of, it's that challenge of complexity which was just exploding in the early 80s that caused a huge amount of things to happen. And the other critical thing that happened that year was the 16-bit microprocessor came out, and you could design workstations. And then you had workstations that you could put software on, and then you had this sort of constantly iterating wheel, building new computers. You could build new chips, you could build new computers, and build new software, and so forth. So
was it a virtuous cycle where the engineering workstations gave rise to more CAD tools, which facilitated higher density computer designed LSIs that gave rise to more, and so on and so forth?
Right.
Was that the case?
Yeah.
Okay.